Hi class, here's our first video on section 1.1 of the textbook covering functions and their interactions. This is a very important section because throughout the entire semester we will be studying functions. That's basically what this whole class is about. So a natural first question to ask would be, what is a function? So normally we would have a class discussion about this because students often have some idea of what a function is. You might not have the full definition, but you, I'm sure, might have a couple of ideas, or maybe you totally forgot. That's okay. So maybe take a second to just think in your mind what a function is, and then I'll give you some of the answers since this is just a video and I can't actually talk to you. Okay, so what is a function? We can have a few different definitions and you can decide which one makes the most sense to you. So the first would be in terms of sets. So if x and y are both non-empty sets, so that just means x and y are maybe collections of numbers, for example. So x is some numbers and y is some other numbers. Then a function is just a relation. So that means a relationship. We'll see later that it can be a set of ordered pairs, but basically you can think of it as kind of like a rule that associates elements of x to elements of y. So a function is a relation with one special property, so such that this relation associates each element of x with exactly one element of y. Okay, so we'll see two more definitions that are basically equivalent, but a function is like a rule or a mapping, however you want to say it, an association, a set of arrows, stuff like that. But the important thing is that every element in x is associated with exactly one element of y. Okay, so another way of saying this is that a function is a set of ordered pairs So an ordered pair is just a pair, like x, y, in which the order matters. So x is first and y is second. So that means x is being associated with y in this function. And then the second part will be that in which no ordered pairs have the same first element and different second element. Okay, so this is basically trying to say the same thing as the first definition, just like in a slightly different way. So each element of x is associated with exactly one element of y, because if not, then one element of x would be associated with two elements of y, so that would be a pair where you have the same x with two different y's, so that can't happen. Okay, so let's just say this one more way, and then we'll see a bunch of examples. Okay, so because a function doesn't have to be given by an equation, but oftentimes, especially in this class, it will be, we can say that a function is a rule defined by an equation of the form y equals f of x. So this would be basically like the same as the ordered pair x comma y. It's just again stating that the element x is associated to the element of y. This notation just means that f is the name of the function. Okay, so we can say that a function is a rule defined by an equation y equals f of x such that, and then now we have to have the restriction, right? For each value of x, there corresponds exactly one value of y. Okay, so hopefully that helps you to know what the definition of a function is. You can just remember it whichever way is easiest for you. So here's like the first example, 1a, pretty intuitive example, not with numbers, but with birthdays. And it's asking whether the following rule defines a function and why. So this is a rule that takes a person, so the person would be x, and it's associating with each person their birthday. So you can think that the birthday is like y, okay? The way the arrow is going is kind of a hint that the person is the input. Sometimes we call that the independent variable, okay? And the birthday is the output. We call that the output is the dependent variable. And of course, it does depend which direction we go. So you might have been wondering about that. So the question is that basically, if we think of like the person as being x and the birthday as being y, well, this is a rule that assigns to each person a birthday, so it does the first part. And then we also want to know, is it true that for each person, for each value of x, there corresponds exactly one value of y, exactly one birthday? So does every person have only one birthday? And you can look and see, we have 5 people here, and they each have only one birthday. So we can say yes, it satisfies the definition, okay? Each person has exactly one birthday. Now you may have noticed by looking at this example that both Lisa and Minomi have the same birthday, September 16th. And as we know, this definitely happens that people have the same birthday. So that doesn't mean it's not a function. We will say later in chapter 4, it's not a special type of function called a one-to-one function. But this example can kind of help you remember the definition too, because we all know that each person has only one birthday, but that multiple people can share a birthday. Okay, so that's kind of like the definition of a function. It just says each person has only one birthday. Okay, so for part B, we're going to write down the relation, or now we know it's actually a function above as a set of ordered pairs. This is just to make sure that if you understand the ordered pair notation. So I'm going to have a set. This little brace means that I'm writing down a set or a collection, and inside of this set is going to be ordered pairs, and the first element is supposed to be the x value, so the person. Let me move this a little so that we can see. So the first person is Lisa, and then the y value will be the birthday. So Lisa's birthday is September 16th. So that's our first ordered pair x comma y. And then we have the next person, which is Paul, and Paul's birthday is January 5th, and so on. We can list these as ordered pairs. So then we have Stacy, June 3rd, Minomi, September 16th, and one more in this example, Latifa, whose birthday is May 28th. Okay, so those are all our ordered pairs, and then I can put the squiggle closed brace to show that I'm ending the set. So this information in part B is exactly the same as the information in part A. It's just represented in a slightly different form. Okay, let's see another example, number 2. Does the following rule define a function and why? So think about, before I tell you, whether you think that this defines a function or not based upon the definition. So this rule, it takes the number of carats in a diamond as the input, and it outputs the price of that diamond. Okay, so if you look here, so the question is, does every value of x, so does every value of the number of carats in the diamond correspond to exactly one price, exactly one y value? And what we can notice in this example is that actually a 0.71 carat diamond has 2 different prices. Okay, so what we can say is that no, this is not a function because one input or x value of 0.71 has 2 different outputs. Okay, one of the 0.71 carat diamonds costs $1,575, and another of the 0.71 carat diamonds costs $1,952. So basically, we could not answer the question, how much does a 0.71 carat diamond cost? That's a way to see that this is not a function. Kind of makes sense because the price of a diamond doesn't depend only on the number of carats, it depends on other factors such as cut and clarity, or perhaps the jeweler at which you're buying it, etc. You can think of other reasons too. So this is an example that's a rule but not a function because one input has two outputs. Okay, so hopefully that helps you to understand the definition of a function. Now, I spoke earlier about independent variable x and dependent variable y, so let me go into that a little bit more. So definition 1, a function only accepts inputs from the domain. So the domain of a function is the set of all possible inputs to the function. Each input gives only one output because we're dealing with a function, and this output is in the range. So the range is the set of all possible outputs or all of the y values. So that's what domain and range mean. And then we have some notation. So in this class, we're going to extensively use both set notation and interval notation. These are just two different ways to represent the same thing, okay? So as I have mentioned earlier, a set is a collection, usually a collection of numbers, but it could be other things such as ordered pairs of people and their birthdays. And the way that we write it is with that brace, which if I was going to read this here, I would say the set of all. So when you see that brace, you can say the set of all. So the set of all, whatever's in the set, such that that vertical line, or sometimes instead of a vertical line, people write a colon, is such that, and then after the vertical line is all the restrictions, okay? And then you don't necessarily read the ending of the set. So just to make sure that if you understood, when you see this one, you can literally say the set of all. So often it'll be the set of all, say x in real numbers, and then when you see this one, you can say such that. Okay, so this will help you. Sometimes I call on you in class to read things, so this is to help you know how to read it, but if you ever don't know, no problem, I'll just help you out. Just let me know, okay? So that's how you can use the set notation. Also, we have interval notation. So an interval, AB, so this is an open interval when we have the round parentheses. This literally equals the set of all x in the real numbers such that x is between A and B. So another symbol that you may have not seen before, I'm not quite sure, is this epsilon right here, okay? So this is just in, or really it's like means it's an element of the set. So that's how you can read that. And then this R, in case if you haven't seen that before, this is the reals, all the real numbers. So that's all the numbers except for imaginary ones. So it's like square roots, fractions, positive, negative, all that, okay? So when we have the open brace, that corresponds, so like here, this open brace, this corresponds to this being a strict inequality. And note that a closed brace changes the strict inequality into, a less than or equal to sign. So for example, if I have the half open interval from A to B, that would be the set of all x in the real numbers such that x is strictly greater than A, but less than or equal to B. And you can combine intervals together by taking their union, denoted by a U, so that just is kind of like an OR, okay? So for example, for number 3, if I want to express the following in set notation, so this is the interval from -5 to 3, union with the interval from 4 to 6, then I might actually like to make a small picture of it, just so that we all understand. So when we have the interval from -5 to 3, so I can imagine a number line, say this is like all the numbers, right? So I have -5, and then I have 3 here. So I'm saying I want -5 to 3. That means including -5, but excluding 3 and everything in between. And then I'm going to union that with the interval from 4 to 6, and then this is a closed, and then this is an open. So this is included, this is excluded. So it's anything in one or the other of these intervals. And so with this picture, it kind of helps me. So I can say that this is the set of all x in the real numbers, such that, so I know that x has to be greater than or equal to -5 and less than 3, or when you have that union, it's like an or x has to be between 4 and 6. And again, I know to put the inequality strict or not based upon whether I have the square brace or the round brace there. Okay, so you can practice using set notation and interval notation. I think that in my math lab, sometimes it will require one or the other, so that's a good way for you to practice. In terms of what I prefer for showing work on the exam, I don't mind actually whichever one you use as long as you use it correctly, okay? So, moving on to problem number 4, often functions are expressed in terms of formulas, as we discussed. They're not exclusively always given in terms of formulas, but most of the time, especially in this class, they will be. So for example, if we let the function f associate any input x with the y value f of x, which is 2x, then we can answer the following question. So I want to make sure that you guys understand when you see this f, that's just the name of the function, okay? And then when you see this x is the input, okay? And then this is, you can pronounce it f of x. So this means the y value that f associates to x. So this 2x here is y. So that's telling you, given an input x, to get the output y, I multiply the input by 2, okay? So for example, if x is equal to 1, then y is f of 1. So according to the rule, I have to take 2 times 1. Okay, so again, f of x, which is y, is 2 times x. So whatever x is, you have to put it in there. So in this example, x is equal to 1. Oh, sorry, x is equal to 1, okay? And so I want to get y, so I have to take this, and I have to put 1 there. So I can say f of 1 equals 2 times 1, okay? Because in this example, x is equal to 1. And 2 times 1 is 2. Okay, now, if x is equal to 0, then y will be equal to 2 times 0, which is 0. And lastly, if x is equal to -1, then y is equal to f of -1, which is 2 times -1, or -2. Okay, so this is just an example of evaluating the function at a couple of points, but I could plug in other numbers too. So when it asks what is the domain and range of this function, so remember the domain is the set of all possible inputs. So the domain is saying what can I put in for x in this equation. So what can x be? So basically it's like saying what numbers am I allowed to multiply by 2? Well, is there any number we can't multiply by 2? I don't see why. So because any number can be multiplied by 2, that means the domain of this function is equal to all real numbers. Any number can be an input of this function. And in terms of the interval notation, we can say that that's all the numbers from -infinity to infinity. Now, the range can sometimes be harder to find, and you have to think, in this case, what are all of the possible outputs or y values of the function? So you're like, what number could equal to 2x? But really, any number could equal to 2x, because say I want 2x to be a half, then x could be a fourth, and so on. So in this example also, the range is all real numbers, which is negative infinity to infinity. We'll see many other examples. The domain and range don't have to be equal, and they don't have to be all real numbers. Okay, lastly, what is the independent and dependent variable? So the independent variable refers to the variable that's being the input. So in this case, the independent variable is x, and the dependent variable is the variable that's being output. So the dependent variable is y, which is f of x, okay? That's our input and our output. I'll just write that down to make sure that it's clear. So x is the input, and y is the output. Okay, good. So let's look at the problem B. We're going to consider the function that defines the area of the circle of radius r. First, this function is given in words. It's kind of like a geometrically defined function, but we want to write an equation that expresses this function. So A is standing for area and R is standing for radius. So I want to know the area of a circle of radius R, and we remember that this is given by the formula pi r squared. So then with this in mind, I can find A of 1. That's saying take R equals 1 and substitute it into the given equation, or in other words, find the area of a circle with radius 1. This will equal pi times 1 squared. 1 squared is 1, so pi times 1 is pi. Okay? So for this problem, what is the independent variable and the dependent variable? So you have to think, what is the input and what is the output? So given the radius, I can find the area. And there's also a hint because it's like before we had f of x, and then you can kind of see that this is like the independent variable is like x. So our independent variable is r, the radius, and our dependent variable is a, the area. The area of a circle depends on its radius. Makes sense. Okay, and then lastly, what is the domain of this function? So the domain is all the possible inputs. So we'll remember that a of r is pi r squared. Okay, so a of r is pi r squared. And we said that the independent variable is r. So when we ask what's the domain, we're asking what possible values of r can be plugged in this function. So at first you might say, well, I can take any number and square it, and I can take any number and multiply it by pi. So I think that the domain is all real numbers. That thinking makes sense, right? But this is kind of a trick question because really, what is r? R represents the radius of a circle. So does it make sense to have a circle with a negative radius? I'm not sure what that would mean. So be careful on this one, like especially with real life situations. Sometimes even if there are numbers you can plug into the equation, they might not make sense in the context, so we must exclude them from the domain. So we can say that the domain of this function is the set of all values of r in the real numbers such that r is at least 0. I'm okay with a circle of radius 0, that's like a dot, but if you don't want that, you can make it r is strictly greater than 0. I think that would also be reasonable. And just to practice, this would be the interval from 0 to infinity. Okay, so that's like some examples that we have here, and then we're going to do a bunch of computations in a moment, so maybe let's just do number 5, and then I'll pause the video and make another video for the second half. So, okay, so for number 5, give an example of a formula that does not define a function. This is also kind of a difficult question. We saw an example of a real-life situation, which was the number of carrots in a diamond, but in terms of a formula, it's like, what is an equation such that when I plug in one value of x, I get multiple values of y? So really, it's kind of tricky, but for example, if you have, say, x equals y squared, that's an equation, But it doesn't really define a function if we think that x is the independent variable, because when I solve for y, I would have y equals plus and minus the square root of x. So for example, if I plug in x equals 1, I would get two y values out, 1 and negative 1. So something like that, it would have to have a plus and a minus on it, is an example of a formula that does not define a function. Okay, I'm going to pause the video now, and then I'll make a second video to cover the remainder of this section.